In this video, we will implement DCGAN from scratch and train it to generate images like the ones you see in front of you right now.
Just another sunny day in Southern California. It's where the people came to play. Don't let them...
Everything that we're going to implement in this video originates from this paper, which is a very important paper in sort of the development of GANs. And essentially what they did is that they used deep convolutional neural networks instead of the fully connected ones that we implemented in the last video. And with the modifications that they did in this paper, they were able to get, really much better quality than what was attained previously. So we're not going to read through this paper, but I'm going to go to the most important part that we're going to sort of need for the implementation part. So first of all, or actually let's look at sort of the figure first. So this is what the generator looks like, right? It takes in some noise, in this case, a 100-dimensional vector, and then it uses conv transpose 2D. So essentially, sort of the opposite of a conv layer, and it instead upscales the image so that it first upscales it to 1024 channels and then 4x4. Then it upscales to 8x8, 512 channels. And it sort of keeps doing that until it obtains 64x64 and then 3 RGB channels. And so the images that we're working with are, as they say here, 64x64 pixel images. All right, so what they used in that network, by the way, this is the generator, and they use the exact same, just opposite approach, using conv layers for the discriminator. So we're going to go through all of that, and I'm going to implement it from scratch. So we're going to see that. But the most important things here is to understand the guidelines, perhaps, of what they did. Since GANs are incredibly sensitive to hyperparameters, and we saw that in the last video as well, then these guidelines are very important to make sure that the GAN is actually stable. So one thing they did is that they removed, or they didn't use any pooling layers, so no max pool, no average pool, and they instead just used convolutions straight through, just only convolutions, so no linear layers as well, which is at this point, remove fully connected hidden layers. And then they also used batch norm in both the generator and the discriminator. They used the ReLU activation function, ReLU activation function for all layers except for the output, which uses the tanh. So this is the this is the ReLU activation in the generator. And then for the discriminator, they used leaky ReLU, and some details on that they explain here. So I recommend, if you really want to understand get all of the details, then do read through this paper. It's going to be in the description. But anyways, they used min batch size of 128. They initialized all of the weights of the network with a normal distribution with mean 0 and standard deviation 0.02. In the leaky ReLU, the slope was 0.2. And then another thing is that when they used Adam optimizer, they used a learning rate of 2e minus 4. So for the beta parameters of Adam, and this, if you're familiar with Adam, we have two beta values. Beta 1 is essentially for a momentum term, and then beta 2 is for an exponential average. And so what they do is that they instead changed the standard value of 0.9, and they reduced it to 0.5, which stabilized training. So I think all of those things are what we need to have read before, so that now when we actually implement this, you'll understand where these numbers actually come from. They're all taken from this paper. All right, so what I'm going to do is I'm going to have one file, which I'm going to call model.py. And here we're going to implement the discriminator and the generator. And then in the training function right here, we're going to implement all of the training setup. All right, so starting with implementing the model, the discriminator and the generator, we're going to do class discriminator. We're going to inherit from NN module. We're going to do our init, self, and as input to the discriminator, we're going to take some images and we're going to take some features D. And So this features D is going to just be the channels that are going to change as we go through the layers of the discriminator. So then we're going to do super of discriminator self and then dot init. And one thing we're going to do actually before we do the init is we're going to define a block. So the block is going to take some in channels, it's going to take some out channels, some kernel size, stride, and padding. So the DCGAN follows sort of a very nice structure in that they have a conv layer, batch norm, and leak URL. So what we're going to do is we're going to utilize that block. So we're going to do NN sequential, and then we're going to do a com2d. We're going to take some in channels. We're going to take some in channels, and we're also going to take some out channels. We're going to send in some kernel size for the conv layer, some stride, some padding. And then because we're also going to use batch norm, we can set bias equals false. It's just an unnecessary parameter. So then we can use batch norm 2d of out channels. And then after that, we're going to use the leak URL. And we're going to do with a slope of 0.2, sort of following the implementation in the paper. All right, so now we're going to do self.discriminator is NN sequential. And in the beginning, I'm not sure if I actually showed this from the paper, but they said that they didn't use a batch norm in the first layer of the discriminator, and also they didn't use it in the last layer of the generator. So sort of just following that, all we're going to do is a conv layer right here with some channels image as input channels. Then features D, we're going to have a kernel size of 4, stride of 2, and padding of 1. So this kernel size, stride, and padding is sort of inferred from the figure that we saw previously. Then we're going to do a leak URL, and we're going to have a slope of 0.2. So we're skipping the batch norm here. But after the initial layer, this is when we can use that block. And so we're going to send in some features D. We're going to have some feature D times 2. And then we're going to have kernel 2, stride 2, and padding 1. So they're sort of utilizing that every time. So we're just going to copy paste that. And all we're going to do is we're going to change the in channels to features times 2, and then times 4, and then times 4, and times 8. So maybe I should just sort of go through the shapes a little bit. So the input shapes is going to be n times channels image times 64 times 64. And then, so after this one, it's going to be 32 times 32. And then obviously, features D as channels. So after this block, then it's going to be 16 by 16, then 8 by 8, and then 4 by 4. And then at the end, when it's 4 by 4, they do another conv layer. So com2d of features D times 8, and then output it to just a single channel. Because remember, all they want here is a single value representing if it's a fake image or a real image. For that, they use a kernel size of 4, a stride of 2, and a padding of 0. So the output here is going to be just 1 by 1. And we're also going to have, so it takes this 4 by 4 sort of pixel values and converts it into a 1 by 1. And it also converts the channels to a single channel. So all that is outputted is then a single value that represents if the image is fake or real. And to ensure that it's between 0 and 1, we're going to send it through a sigmod layer at the end. All right, so that's pretty much it. We got to do one more thing, which is define forward of self and x. And all we do is then return self.discriminator on x. So that's sort of the entire discriminator. And we're going to do a very similar thing for the generator. All right, so class generator, inherit from NN module. Then we're going to define our init. So define init of, and then we're going to send in set dimension, the noise dimension. and then channels of the image, and then features G, similar to what we did in the discriminator. Then we gotta call this super method. So super of generator self init. Then we're gonna do, let's see, self.net is nn sequential. And we're gonna do, I guess, a very similar thing here. So let's do the block first. So block self, it's gonna take in some in channels. It's gonna take out, send out some out channels, kernel size, stride, and padding. All right, then we're gonna return nn sequential of, and instead of using a conv layer, we need to upscale it. So that for that, we're gonna use nn conv transpose 2D. And I'm not going to go into more depth on exactly how a transpose convolution works. You can just sort of view it that it does the, I guess, sort of the opposite of a conv layer. So for the conv transpose 2D, we're going to send in some in channels, some out channels, some kernel size, stride, padding, and then we're going to set bias equals false. Just because we're going to use a batch norm, and when we use the batch norm, we don't need to use the bias. So we're going to batch norm 2D, we're going to send in some out channels, and then nn relu. And so why we're using relu here is just we're copying the DCGAN paper. So all right, now that we have that, we can use that in our generator. So in the generator, we can actually use batch norm in the beginning. It was only for the discriminator that we couldn't do that. And then they instead didn't use a batch norm for the last layer. So we can do self.block, and we can do set dimension as input, features G, and then times 16, kernel size 410. So what's going to happen here is that we have some input that's n, where n is the batch size, and then we have set dimension times 1 times 1. And what happens here is that this makes it into, I guess, and this makes it into n times, fg times 16, and then times 4 by 4. So really what's important here, I guess, is the image values, the pixels. So it's going to be a 4 by 4 after that block. And then we're going to have another block where now the input channels is going to be feature channels times features G times 16. And then we're going to have kernel 2, stride 2, padding 1. And so what's going to happen here, it's going to be 8 by 8. So if we copy that thing and do it again. Oh, and we need to, of course, also have right here, we're going to have features G times 8. And then this right here is going to be features G times 8, and then features G times 4. And one thing I actually realized now is that it might not make much sense why we're doing this times 8 and times 4, but all of these are really interpreted from the figure in the paper. And so what we're going to use for all of this to make sense later on is features G and also the features for the discriminator, features D, are going to be equal to 64. And if we do that and we do all of these we do these computations for each channel, the numbers just tend to, they just work out. So really this is just looking on the figure and then trying to interpret what the channels are going to be. And they then follow this nice structure that if we use features G to be 64, then we can half it to be times 16, then times 8, and then times 4. All right, so let's do that one more time. And we're going to now do features G times 4, features G times 2, and now it's going to be, so here it's going to be 16 by 16 by 16. Here it's going to be 32 times 32. And now for the final one, we don't want to use the block because we don't want to have the batch norm. So we're going to do conv transpose 2D, features G times 2, and then we're going to have channels image, kernel size 4, stride 2, padding 1. So very similar to what we did above, and this is going to be 64 times 64 output. And what we're going to do after that is just an tanh. Very similar to what we did in the last video. We're using tanh because it's going to make the output to be -1 and 1, which is exactly what we're going to normalize the images to be within. So since the images are normalized to be within this range, we also want to make sure that there are model outputs in a similar range. All right, so hopefully this works now. So what we can do is, oh, actually, we need to do one more thing. So we need to also create a function to initialize the weights of a particular model. And so, we need to do it as they did in the DCGAN paper with mean 0 and standard deviation 0.02. So what we can do is we can just for m in model.modules, and we can check if and I just realized that we don't have to do it in this way. We can just do nnconv 2d, nnconv transpose 2d, and then we can do nnbatch norm 2d. Since they're all going to be initialized in the same way, we can just then remove those two additional if statements. All right, and then let's just do a test. So test, we're going to set n in channels height and width to be, let's say, 8 examples. In channel is going to be RGB 3 and then 64 64. Let's set our nose. Let's set the set dimension to be 100, and let's generate a torch random of n in channels height and width. Then we're gonna initialize our discriminator. So discriminator of in channels and then 8 for the features G. Then we're just going to do initialize weights of discriminator and then assert disk x shape. And we want that shape to just be n, 1, 1, 1, right? Because we just want one value per example. All right, so let's just try and run that first of all and make sure that that works. And it did. So what we can do then is our generator. So generator of set dimension and then in channels and then features G to be 8. Then let's generate some sed. So just the latent noise. It's going to be n set dimension 1 1. And then we can assert that the generator of that when we input that noise, that shape is going to be n comma in channels and height and width. So if we run that and it doesn't produce any error, let's just print success. Oh, okay. So for the generator, we forgot to do the forward. So define forward, self and x, and then let's not call it net. So let's call it gen. All right, so then all we have to do is just return self.gen of x. So let's run that again. And let's also try to do initialize weights of that generator. And it works. All right, so that's it for the model architecture. And hopefully you were able to follow. The only, I guess, tricky part is sort of understanding why this works. And for that, you might have to compare with the paper and then make sure that, go through it step by step and see that, okay, those channels match, and then, go through it line by line. All right, so here we're importing all we're going to need for the training setup. And all of these are pretty basic. And we're also importing, from model, we're importing the discriminator, generator, and also the initialize weights function. So I'm actually going to code all of this from scratch. I'm not going to copy paste any code, but a lot of the things that we're going to do now is very similar to what we did in the last video when we built our very, a simple GAN. But so it might be good for repetition nonetheless. So we're going to do device is torch.device. So we're going to set up hyperparameters, etc. We're going to set CUDA if torch.CUDA is available. Otherwise, we're going to set the CPU. Then we're going to do the learning rate is 2e minus 4. Just copy paste it from the paper. The batch size is going to be 128. Just copy paste it from the paper. The image size is going to be 64. The channels of the image is, let's set 1. So we're going to do first for the MNIST data set. So we're going to do that, and just to, see that it produces something that looks good, and hopefully something that's much better than what we got in the last video. And then we're also going to train this on a celebrity data set, but I'm going to show you how we add that later. We're just going to modify 2 lines at the end. Then we're going to do our set dimension is going to be 100. The number of epochs, let's just run for 5 epochs. The features disk is going to be 64, and the features gen is going to be 64. And we need to set 64 for both to match the exact same for what they did in the paper. All right, so after that, we're going to set up some transforms. So transforms.compose. We're going to do transforms.resize to image size. Then transforms to tensor. And then transforms.normalize. And we're going to do 0.5, 0.5. For my experiments, this works a lot better than doing the exact mean and standard deviation. So we're just going to use that. Actually, I'm going to do it like this in a list instead. And I'm going to do it for, underscore in range of channels image. So I'm going to do the same thing for this one. I'll explain why I'm doing this in just a second. So 0.5 for underscore in range of channels image. So basically, why I'm doing this is just so that when we change this to 3, when we're doing for the other data set, then we don't have to modify this normalize. It's just going to be a sort of general, no matter what the channels image that we set. All right, then we're going to set the data set, and the data set is just going to be MNIST. Root is going to be data set. Train is true. Transform equals transforms. And then download equals true. The data loader is then going to be data, or we can just call it loader. It's going to be data loader of data set. Batch size is going to be batch size. Shuffle equals true. Then we're going to do the generator. So I'm going through this a little bit quickly, I guess. This is sort of what we did in the last video, and none of this, this is just some simple code. So we're going to initialize the generator now. So generator of noise dimension of channels image, and then features G. Features gen, I guess is what we call it. And then send that to CUDA. And the same thing for the discriminator. So discriminator, here we're going to send in the channels image, and then the features discriminator, and then to device. So, the features generator and the features discriminator are going to be equal. So you could just use one, but, just to make sure that you separate them, and you could use different channels. Then we're going to call initialize weights on the generator and initialize weights on the discriminator. All right, so then we're also going to set the optimizer to be optim.atom of generator.parameters. We're going to set the learning rate to be learning rate. The beta values, and this is important, this is from the paper, we're going to set 0.5, and then the standard is 0.999. So we're just going to keep that one. All they wanted to change was the beta 1 value. And opt discriminator is optim.atom discriminator.parameters. Learning rate is learning rate. Betas is 0.5, 0.999. Okay, then we're going to do the criterion. Our loss function is going to be nn.bce loss. Okay, so then we're going to do, pretty similar to what we did in the last video. We're going to set some fixed noise so we can see the progression as it trains. and we're going to do torch.random 32 set dimension. Oh yeah, so this, when I sent in the noise, we're going to do set dimension here because that's what we called it up here. All right, so set dimension and then 1, 1 and send that to device. We're going to have a writer for TensorBoard. So summary writer. We're just going to set it to logs and then real. And let's copy that and make another one for the fake ones. So this is going to be logs fake. And we're also going to need a step for printing to TensorBoard. And then set both of those networks to training mode. They should be by default, but for some reason if they aren't. And now for setting up the training, we're going to do for epoch in range of num epochs. And this should be capitalized on num epochs. Then we're going to go through for batch and then real. And we're not going to need the actual labels. So I'm just doing an underscore here because training GANs is unsupervised. So then we're going to do enumerate of loader. And we're going to need to send real to device to make sure that it's on the GPU and generate some noise by doing torch random of let's see, batch size, noise, set dimension, and then 1, 1, and then dot to device. And then we're going to train the discriminator. And this is to maximize log of d of x, and then plus log 1 minus d of g of z. And so if this is the first video that you're watching, then I'm explaining this in much more detail in the previous 2 videos. So I'm going to go through this much more quickly. So if you're confused over this, the training part, specifically when we train the discriminator right here, and then the generator, then watch those videos. So discriminator on the real is going to be discriminator on real. Then we're going to just reshape that to just be, a single value for each example, so that we don't have, n times 1 times 1 times 1, so that we only get n. We're going to get the loss on that discriminator of the real. So that's criterion of discriminator real torch ones like discriminator real. Then we got to do on the fake one, so discriminator of fake, and then dot reshape -1. Loss discriminator on the fake ones. It's going to be criterion of fake, and then torch zeros like disk fake, and disk dot zero grad. Loss disk, but we gotta get loss disk is loss disk real plus loss disk fake, and then let's just divide that by 2. You don't have to do this, but I don't know, just kind of makes sense. And then loss disk is dot backward and opt disk dot step. All right, so that's for training the discriminator. Then we're gonna train the generator to minimize log of 1 minus d of g of z. But as we talked about in the last video, because of gradient, saturating gradient problems, this is the same thing as maximizing log of d of g of z. So we're gonna do output is discriminator of fake. Oh, by the way, one thing we need to do here is retain graph equals true. And the reason why we got to do retain graph equals true is because we're going to reutilize this fake in the second part, but PyTorch is going to remove the intermediate results because we did loss out backward here, and fake was used in this computation. So that's why we're doing retain graph, so that we can reuse that when we're training the generator. So then let's do reshape -1. Let's calculate the loss on the generator, which is criterion of output torch ones like output, and then generator dot zero grad loss gen dot backward, and then opt gen dot step. Okay, then I'm gonna copy I said I wouldn't copy paste code, but I'm actually going to copy paste this code because this doesn't say much. So I guess I can explain it. So occasionally, we want to print the loss. I'm not really sure why we want to do that, to be honest, because, the loss doesn't say anything when it comes to GANs. So I guess we can just remove that, or the printing of the loss. But anyways, what we're doing here is we're just doing with torch.nograd. We're generating some fake images on the fixed noise, and then we're just using Torch Vision utils to make a grid of images, and then we're writing that to the tensor board. So that's pretty much all we're doing, and then we gotta update the step variable because that's what's used to sort of see a progression of the images. But that should be it for the training and the model. So let's run this and let's hope that it works. All right, didn't work. So let's see, available. So this should be available. All right, fake is not defined. So let's see, fake. Yeah, so we're using fake right here, but we need to, of course, generate those. So we need to call the generator on that noise. So now we have the fake images. Oh, and I made a mistake here. We're gonna send, take the loss of the discriminator fake, and then, torch zeros like discriminator fake, because we're training this part right here. So we want to take the discriminator on the generated fakes. All right, so this is the result we get after running for about 5 epochs. And I would actually have liked to run it for a little bit longer because some of these don't look that good. Some of them look pretty good, and then some of them can definitely be improved. But nonetheless, they look incredibly much better than the ones we got when we use a fully connected network. So maybe that's something you can try out, just running it for longer. Can we get something that looks better than this? But what I want to do now is, all right, so what I want to do now is change the dataset to this CelebA dataset. And so basically what we have is just a bunch of images on celebrities, I guess. And then what I have is that we are going to have a folder, celeb dataset, and inside that we're going to have just another folder with images. And so why we're doing it that way is because then we can use the dataset's image folder, and that's going to just automatically load it for us. So what we can do is just, I guess, comment out that part, then do another dataset equals datasets.image folder of root celeb dataset, and then transform equals transforms. And that's all we need to change. And also the channels image is going to be 3 now. But other than that, everything stays the same. Just one thing is that if you want to also run on this data set, I had some difficulty downloading it, so I'm just going to upload it to Kaggle, and I'm going to have a link in the description of the video, and you can go download it, and you can just follow the steps that I'm doing in this video. All right, so let's just run it and train it on the CelebA dataset. All right, so I stopped the training now because I really want to finish this video today. But I let it run for about 3 epochs, and so this is the results that we get. Obviously far from perfect, and we don't really expect it to be that great. But I think that if we train it for just some more epochs, then it would look even better. But really just, this is a hard task that we're asking it to do. And hopefully, we're going to see, with more advanced architectures in future videos. and to really get, better performance. All right, so I really hope that you were able to follow the steps of the video and understand DCGAN and its implementation. So DCGAN works a lot better than the network that we implemented in the previous video, but it still suffers from being, really, really sensitive to hyperparameters. And I really encourage you to try training DCGAN and try to play around with the hyperparameters, and you will really see this fact. So in the upcoming video, we will try to focus on how we can improve the stability of GANs. And then in future videos, we will try to implement more close to state-of-the-art architectures. But anyways, thank you so much for watching this video. I hope to see you in the next one.